My name is Aris. I'm Professor of Astrophysics in Oxford. I'm a co-PI of the pulsar search and the offline pulsar timing component of the SKA. And I'm also a co-PI of something called the 1,000 Pulsar Array project on Meerkat. And it's kind of a combination of these two with emphasis on the second that is informing most of my talk today. And the point of my talk is to sort of demonstrate the role a telescope like Argos could play in the era of SKA. John, I noticed the previous speaker did not have the camera on. Would you like me to have my camera on or off?
I think it's up to you. You can, if you do turn your camera on, then I can also show your face, because right now we only see your presentation.
Okay, so
but for the people online, I guess, yeah.
Let me see. I can do that. Well, I should have done it before I started, I guess, but never mind.
It's fine. Yeah, no worries.
No worries. Yeah. Okay. I'll show you my face at the end so you know who I am. All right. So, I'm talking about slow pulsars, not the type that the people talking about pulsar timing arrays are talking about, non-recycled pulsars, ones with the spin period typically above tens of milliseconds. And so in the PP dot diagram that you've seen, I'm talking about this population here. Could you just tell me if you can see my cursor?
Yes, yes.
Okay, great. So the reason I'm interested in these is that there are still fundamental open questions about this population. And in fact, the SKA is going to try and find all of the galactic pulsars, which hopefully amount to several tens of thousands. And hopefully with these large populations, we'll be able to answer some of these questions, like what the birth properties of pulsars are, like their birth period and magnetic field, and how do these things evolve with time. And in order to understand what we're actually seeing from the radio emission of pulsars, it would be good to try and understand the geometry. So by geometry, I mean the inclination angle between the magnetic field and the rotation axis, and the angle between the line of sight and one of those two axes. And so what is the beaming fraction? How much of the sky do pulsars illuminate? Also, we don't really understand what the birth rate of pulsars is. In other words, we don't really understand whether the different subgroups of pulsars that you see in this PP dot diagram evolve into each other, or they have different channels of formation. And that's kind of a crucial bit of the puzzle that's missing. And we don't really yet have a clear answer to whether the radio emission, which, don't forget, is the carrier for all the physics that we can do with these things, if the processes for radio emission are the same between MSPs and slow pulsars. Another thing we don't understand is how bright these things are, and especially when we try and put them into some sort of context relating to FRBs and the extragalactic population of FRBs and so on. Do we understand the radial velocities of pulsars when we're making these comparisons? And don't forget that pulsars are really good labs for studying the configuration of cold, dense nuclear matter. And the question from the magnetospheric point of view is how these peculiar interiors interact with the magnetosphere. So which of the magnetospheric processes that we see can we connect to the extreme interiors of neutron stars? There have been long-standing programs at Jodrell Bank and Parkes in particular of pulsar monitoring, so monitoring a large population at a regular cadence. And these have been very successful in identifying a whole host of phenomena, new phenomena that shed light on the whole pulsar problem. And so we also want to understand the key components of the physics of radio emission that arise from observations of individual pulses. So there's an enormous wealth of information that comes from individual pulses. And how can we, an open question that has always been there is, how do we actually reconcile the complexity of the single pulses with the stability of average profiles? So continuing on the motivation for slow pulsar monitoring campaign, the reason we use millisecond pulsars for gravitational wave searches and the likes is because young pulsars have very high timing stability. So owing to their moment of inertia and their very fast period, and to the fact that there are less sort of anomalous, fewer anomalous phenomena. But there is an order of magnitude more slow pulsars than there are MSPs. And so among these slow pulsars, there are corner cases, let's call them. So pulsars that show very clearly, that manifest very clearly a particular phenomenon. And so that gives us a lot of sources that we can use to target specific questions. Also, slow pulsars have a larger spin down rate, as you can see on the PP dot diagram. And that means that we can make multiple measurements of the spin down rate, or the period derivative, or the frequency derivative, within a reasonable timescale. And that allows us to measure, or to try and measure, the second derivative of the spin frequency. And it's the second derivative that tells us something about the dominant mechanism that's responsible for the spin down. So these efforts have revealed that there are pulsars that switch state. So they switch between two well-defined values of the spin down frequency. And they've also revealed that not a lot of pulsars show what we call the canonical breaking index. So the relationship between the frequency and its first and second derivative doesn't support the idea that pulsars are slowing down because of magnetic dipole breaking. And that's quite a fundamental thing. In fact, on this PP dot diagram that I'm showing here, you can see all these diagonal lines. So there are diagonal lines that go in this direction, and they have values of magnetic field on them. They assume that the pulsar is spinning down because of magnetic dipole breaking, and that assumption gives you the value of the surface magnetic field. And so if the assumption is wrong, then this is also probably not exactly right. And these lines here along this direction show you the lines of constant characteristic age, which also assume that pulsars are spinning down on average due to magnetic dipole breaking. Anyway, the other reason to look at slow pulsars is that they probably span quite a large age range. If you believe characteristic ages in this diagram, they span over 10 to the 9 years. And that means that there are different age groups here, and each of them is reasonably well populated, so it can be studied individually. And the other thing that you gain by having a large number of sources is that they probe many galactic lines of sight. So if you're interested in the interstellar medium, I say if you're interested in this, if you're studying pulsars, it's impossible not to be interested in this, because it's one of the things that affects the emitted radiation and results in the observed radiation. But if you're interested specifically about the properties of the ISM, then these lines of sight allow measurements of the rotation measure, dispersion measure, scintillation, etc. Oops. There we go, 2, 3. Okay. So a coherent monitoring program with a single instrument using a single backend and a single processing pipeline can provide a catalog of parameters that is coherent and that can be used for theoretical studies down the line. This is something that is problematic with the pulsar catalog at the moment, because it's accumulated so many parameters that are derived from inhomogeneous studies at a variety of telescopes with a variety of backends, receivers, different bandwidths, different software reduction. And so it's very difficult to compare one survey with the other. So for the survey that I'm talking about on Meerkat, well, Meerkat is a fantastically sensitive telescope, as you probably all know. And also when you have a new fantastic telescope, you always make discoveries. So I presume you all know that Meerkat is one of the SK pathfinders for the mid frequencies, so not the low frequencies, but the frequencies say above 0.5 gigahertz or so. And it consists of 64 aperture dishes with an effective diameter of about 14 meters. Most of the work that I'm talking about today uses the L band, and that's a receiver with a bandwidth of 856 megahertz from 856 to 1712 megahertz. It's a fantastically sensitive receiver with a very low receiver temperature and a system equivalent flux density much better than Parkes, which was our go-to instrument up to the time when Meerkat became available. And so part of the reason to do this is that we also need to be able to conduct timing surveys of large populations when SK comes along, and that involves scheduling, calibration, data management, and so on. Each of these things is an easy phrase or word to write, but a difficult thing to do in practice. And so we need to be able to do these things for large populations. So interferometers for pulsar monitoring, well, as you all probably know, this or most of this these days relies on having very good software. And it's kind of the state of the art these days that you can do successful pulsar monitoring campaigns with interferometers like we do with Meerkat or with LOFAR and other telescopes. But these are my thoughts of what you need in order to put together a successful pulsar monitor. And this is, the context of what Argos may be designed to be. So obviously the things to keep in mind are the primary beam size. So I'm just giving for reference here, if you have a gigahertz, if you're observing at 1 gigahertz with a 1 kilometer baseline, that gives you about 4 square degrees for a 10-meter dish and 1 square degree for a 20-meter dish, etc. And if you consider that there's 1 pulsar per square degree on average in the galaxy, that'd be, well, let's say 1 to 10, I should have said here, that the SK is going to find, then you need some ability of your instrument to generate tide array beams. And that requires phasing up the instrument to produce tide array beams, and that implies an overhead on the observing time, and it implies stability beyond what the ionosphere allows you to do. You probably also need some ability to form subarrays. So if you have a large number of elements in your interferometer and you have sources with a variable or a variety, let's say, of fluxes, then you want to be able to observe the very bright ones with a smaller part of your array. And perhaps at the same time, you want to be observing the weaker ones with a larger bit of your array. So you want to subarray, for sure, in order to make best use. You need to be able to ingest coherent data with your computers. So you need to be able to ingest baseband data, which includes phase information, and that depends on the bandwidth, but these days, several tens, I guess, of gigabits per second is relatively easily doable. and also doable is coherent dedispersion. So all the sources that monitoring campaigns track are known sources with a known DM or approximately known DM. And a standard online pulsar timing backend these days will coherently dedisperse to maximize the signal to noise. If you're studying pulsars, in order to understand pulsars, one of the key diagnostics is measuring the polarization. So you need to be able to calibrate your system. So if you're producing a single tide array beam, then that tide array beam is probably on the axis of the primary beam, unless you have some tendency to make life difficult for yourself. But the thing is that if you're trying to monitor a large number of pulsars, and presumably a few of them fit within your primary beam, and you want to be monitoring them simultaneously, then you need off-axis polarization calibration for the other tide array beams. And this is something that is being actively worked on around the world, but I wouldn't say it's an entirely solved problem. So this is something that requires effort. And you need to consider what calibration schemes you're going to use, including parallactic angle tracking, feed rotation, or whatever. And that also has implies some considerations for orientation of your feeds in the first place, and the ability to do per antenna polarization calibration. So this is a general problem. It's not unique to whatever design Argos will adopt, but it's something that you need to keep your eyes on to make sure everything works properly. And I would say something that's generally not paid attention to enough is flux calibration, and that's necessary also for observations that aim to understand what pulsars are and what neutron stars are. So that means including a noise diode or some other working solution for flux calibration. So the other list of ingredients of a successful pulsar monitor are to understand the integration lengths you need for your targets. So pulsars are variable sources, and you need to be able to take observations that take that intrinsic variability into consideration. For example, by optimizing a shape parameter. So our 1000 pulsar array paper 2 describes how we did that in order to come up with an optimized integration time for each source. The second is understanding the appropriate cadence to measure time variable phenomena. So for example, if you're looking for glitches, profile variability, spin down variability, break index, and so on, all of these processes have different intrinsic timescales, and you need to be able to design your survey so that you maximize your results. There's some work that you probably need to do to dynamically update the list of your targets. So assuming you can't monitor 10,000 pulsars regularly because the time demanded is too high, you have to decide what criteria you're going to put most emphasis on. So for example, you could choose sources that are known to show some peculiarity over sources that are known to be very sort of regular, constant behaving. Or you could choose the opposite. You could choose to emphasize discovery in sources that are not. I think the previous speaker also mentioned that RFI is a big deal, and you need to be able to remove RFI, and RFI is only getting worse, mostly due to airplanes and satellites and remote locations and telecommunications. So also for a program like this, some coordination with schedulers and scheduling is necessary. You need the ability to react. So for example, if you're monitoring a large number of sources and you find all of a sudden one source is doing the thing that you were always interested in observing, that then requires an increase in the cadence, let's say, or an increase in the integration time. So you need to be able to do these things on a relatively short time scale and on demand. And finally, one of the if not the key advantage of doing this with an interferometer, is that interferometers are built to create lovely images now, even in the radio. And somehow our ability to simultaneously generate images together with timing data has been underused and underexploited up to now. And I would say that that's one of the key new things going forward in the future. So this is my idea of the ingredients for a successful pulsar monitor. So for Meerkat, the 1000 pulsar array, we're producing some legacy data set. Here's some colorful plots. So one legacy data set is the time averaged properties of pulsars, where we have about 1,200 pulsars. And we've already published this paper this year. We actually measure very, very carefully quantities like the luminosity, the polarization, the pulse width, the spectral index, etc., etc. And this gives you a catalog of uniformly measured and uniformly processed data. The second legacy data set is a catalog of a very large number of single pulses. So we have over 1 million single pulses from over 1,000 pulsars. You can think of it as roughly 1,000 pulses per pulsar for 1,000 pulsars. And what these plots show you here, although I'm not going to get into the details, but I'm just going to talk about this plot at the top here. It shows you that the well-known phenomenon of drifting subpulses, where individual components of individual pulses appear to drift in rotational phase from one period to the next, is clearly a signal-to-noise dependent thing. So for higher signal-to-noises, the fraction of pulsars that show this phenomenon seems to be plateauing at around 60%. And as you drop in signal-to-noise, the observable fraction also appears to drop. So that clearly tells you something about the fact that you're not counting properly, and that if you had more signal to noise for these pulsars here, they would probably also be drifting. So we are just about now putting out, after 4 years of this program running, we're putting out our first paper on timing results with updated ephemerides of 597 pulsars. So on the figure on the right there, you can see the 597 pulsars, I think, are the blue dots. The entire 1000 pulsar array sample is the pink dots. So you can sort of see that it's an unbiased sample. It's all the pulsars that we can see with good positional accuracy from Meerkat. And the other dots are the entire population. And so now we have data to publish something like a figure on the left for 597 pulsars, which includes timing residuals. It includes a time variable spin down frequency, which in this case shows an interesting bump. It includes flux density monitoring over time, and DM and RM monitoring, which in this case both show a monotonic increase. And the other paper that we've just submitted is it specifically looks at the average pulse profile of the 1000 pulsar array pulsars, and it focuses in particular on 7 pulsars that seem to have interesting profile variability. So the plot here shows you, it's a difference map. It basically shows you the difference between the observed profile and a constant template as a function of rotational phase and time over 3 years of TPA data, or 3.5 years of TPA data. And this shows you a shape parameter in these black dots here, which is somehow constructed using the profile total power data. And in the green line here shows you the spin down frequency, so nu dot. And as you can see in this case, there is some correlation between the shape parameter and the spin down. And so the question here is, do all pulsars show at some level this correlated variability between their profile and spin down? And what does that mean in terms of our ability to do high precision pulsar timing? I was planning to show you a gallery of results from the TPA. I'll just do this I'll race through this literally. So we have data from giant pulses from the original giant pulse emitter in the LMC, the crab twin, as some people call it. The interesting thing here is that you can see that we have band limited or narrow band giant pulses that really resemble FRB pulses, and you can see the references at the bottom here. We've observed, as part of our catalog, pulses in the magellanic clouds, and that gives us very good estimates of rotation measure, scattering, and DM relationships. We measure the pulse widths across the entire population, and that gives us some ways to try and estimate the emission height above the surface of the star, what sets the size of the polar cap, and whether the emission height is more or less constant and independent of the spin period. So you can do this on a population basis with this large number of sources and this uniform way of processing them. We are interested in polarization, so we've looked at the polarization of young pulsars, which tend to be highly linearly polarized. They're also high E dot pulsars. So E dot is the third line on this PP dot diagram that I didn't mention, and it's the one I believe in the most because it only depends on the moment of inertia and the actual measurements of P and P dot. And so, the conclusions here are that high E dot pulsars also imply high linear polarization, and that we think we understand high linear polarization to be set by orthogonal modes, and therefore does high E dot imply high emission height. We can do time domain measurements of scattering. So scattering just means that we have pulsars that are perfect point sources, and we have multipath propagation, which results in a profile that, instead of a Gaussian or a very narrow peak, it obtains this large exponential tail, and we can go and measure this, and that tells us something about the interstellar medium and whether we have structures in the ISM that are causing the scattering. And we can measure scintillation also using the fact that the pulsars are, again, perfect point sources, and that there are always relative motions between the pulsars in our observatory and whatever it is that's causing the scintillation in the intervening stellar medium. Again, talking about the polarization, we can measure the angle of polarization, and the angle of polarization tells us something about the structure of the magnetic field. So we can do very, very detailed studies with high quality data that are very well calibrated. So what are the next steps for this program? Well, as I said, we are now publishing this paper with updated ephemerides and time series of DM, RM, flux density, and spin down rate. We're also publishing a paper very shortly about the galactic B field based on rotation measurements from this large number of pulsars. And we're also nearing the completion of a paper that addresses the question of similarities and differences between the MSP and slow pulsar population. Meerkat, in the meantime, has a fantastic UHF band receiver, so we're concentrating now on similar studies with that at that frequency. And for the single pulse data, we're going to publish a paper soon containing the statistics, the energy statistics of single pulses, and scintillation measurements of a large sample of pulsars. So Meerkat also simultaneously stores the visibilities, and in principle, there's potential to obtain the imaging data, but it's such a difficult process, such a large volume of data, and so difficult to actually do in practice that we haven't actually done this yet. So I think some thought needs to go into this before you start an experiment of this sort. So this is the final slide. So when the SKA comes online, if we're going to do all the fantastic science we're talking about doing with the SKA, especially when it comes to understanding things like neutron stars, having discovered the entire galactic population. Well, we need a, I would argue, more than one. We need several Argos type instruments. So by Argos, I mean sensitivity has to be comparable to SK. Availability of time has to be there. And, some of the considerations I mentioned earlier have to be there in order to be able to do this. So that's all I had to say. Thanks very much. Lots of people produced work that went into this talk, so they're all mentioned here. And yeah, thanks a lot.
So thank you very much, Aris. Very nice. Five. So very nice overview. Are there any questions for Aris? First, from the online audience. So I see. So Wei here has a question. So Wei, you can go ahead, and I will try to repeat the question.
So it's Wei. So I missed the part that how do you make your selection criterion for this 1,000 pulsars, like other than the periods and the certain sky, and also you differentiate the population from the galactic plane, high latitude, and the population inside the global clusters.
So how much of that was audible?
Not much.
Right. So I think the first question, there were two components in the question. The first one was about the selection criteria for the 1,000 pulsar array sample, and the second one was about any differences between high galactic latitude and low galactic latitude pulsars.
Global clusters
and globular clusters as well.
Also, okay, so first of all, we're talking about slow pulsars, okay, not MSPs. Secondly, the criteria for selecting the population where they have to be visible from the Meerkat site, so they have to be above or below, let's say, a declination of, I don't know what it is, maybe 15 or something like that, not too low for the Meerkat sky. But other than that, it's all slow pulsars that adhere to that have a known position to within arc seconds. So that's the selection criterion. And regarding galactic latitude, well, I mean, that's an unbiased sample of the entire population. So you can do whatever you want with it, and you can't do much better than that. I'm not sure what else I can say about the galactic latitude question.
What about global clusters?
And what about globular clusters? We is asking.
How many slow pulsars do we know in globular clusters? I don't really know.
Or there's zero?
Not much. Yes, not much. Okay.
There's like something like 10 or so.
Yeah, so they're probably, or they're probably in there, but they're not like an object of focus like the MSP populations.
So I have a question about your definition of slow pulsars. So why specifically on slow pulsars? Because I mean, there's many objects that are not particularly covered in PTAs, and they're not used for gravity experiments. I'm thinking out loud here, but there's a lot of these like disrupted radio pulsars that are isolated. They have spin periods of like 100 milliseconds. So, I mean, are those not interesting for your study? Or, I mean, and there's also kind of binaries like 0655 or 465, which is like 192 milliseconds. There's a lot of those things. Do you exclude binaries, or are they included?
No. In fact, I think I'll have to go and check, Paolo, but I think the answer to that is that we have everything in there that isn't an MSP part of the the equivalent PTA campaign. that conforms to the criteria that I just mentioned a minute ago. I don't think there's anything else. So it's not specifically, slow pulsars. It's just that the vast majority of those are the slow population. Yeah.
Right. I think that makes more sense, because if one really wants to be unbiased, you should include things that are the border. Yeah.
Well, exactly. It just makes the description, 3 times longer, and for a very small addition. But yeah, you're right.
Yeah.
Okay, I think we can turn this into the final discussion session, and I think other people can also chime in. But I think I have a question about the point that you made about having this imaging capabilities as well. So could you perhaps elaborate a bit on that? I mean, what would be the obvious added value of doing imaging, and also how well do you have to do imaging if you want to?
Yeah. So I didn't really spend too much time on it, but I showed an example of a pulsar that has profile variability and spin down changes that appear to be correlated. And there are some extreme examples of such pulsars where, the spin down rate changes by tens of % within a very short amount of time, and something seems to be changing in the pulsar profile as well that's quite dramatic. I would really like to have environmental data simultaneously with that kind of thing, just to sort of complete the picture. Somehow we always think of the thing that we're interested in pulsar astronomy, we think about it in vitro, and somehow it doesn't exist like that. There's all sorts of things happening simultaneously. Pulsars are super high velocity objects plowing through the ISM. What's happening? Is there anything else that's happening that is revealed through some other domain that explains our data, rather than me going to, trying to invent new parameters to a complicated timing model or a complicated interior model in order to explain, some external parameter like a small planet crashing onto the pulsar or something like that. So anyway, I'm not saying that you'd necessarily see that through imaging, but I'm saying that imaging adds another orthogonal dimension to your data. You asked me another thing about how good the imaging has to be. Well, I mean, how good the imaging is depends on how many elements your interferometer has and how well they're spaced out, I guess. Because we're talking about, we're talking about snapshot imaging here, right? We're talking about short duration observations of pulsars.
Yeah, exactly. So I was more thinking about, how well would you have to do your imaging to actually, for it actually being useful, which is sort of, I guess.
Anything's better than nothing, I would say. For example, imaging without high fidelity and high resolution and so on, it gives you flux much better than the time domain data. Okay, so even at that level, if you're trying to study scintillation, and what the consequences of that is, so you remove it from your explanation, you need the imaging. So let's start from the flux and then go to more exotic things like what I said before.
Right. Okay. I see. But then you would need to resolve you will need to be able to resolve the pulse as well with your images. So you need really high cadence.
What do you mean resolve?
So resolve the pulsed phase of the emission with the off-pulse phase of the emission.
Oh no, you don't need that in imaging. That's the whole point of imaging. That you compare the pixel where the pulsar is to all the other pixels that are on blank sky.
Right. Okay.
Just a quick one. I guess you look systematically also for giant pulses and stuff like that. I think you mentioned something like that, right?
Yeah.
All right. Mm-hmm.
And yeah, so I also left a question for you in Slack, but I can probably
sorry.
but I can probably repeat it. I can ask it now. So so you showed this very beautiful timing results from your monitoring campaign.
Yeah.
So just to connect back to what Paolo was saying, have you perhaps searched for binaries in or multiple systems in your data?
Not binaries that you would really see anything dramatic in the timescales that we have. No, I don't think there are. Well, that's yeah, I don't really. We haven't discovered new binary systems, so I can't really tell you how many of there must be a small population of slow period binaries in there as well. There's nothing particularly new about them.
So perhaps then you can improve on Dunk's paper on the prevalence of binaries on hidden binary.
That's a good point. So yeah, that's a good point.
Yeah, and the other point I wanted to make about that is that there are also some. So I had a look at this a few years back, and some of this, apparently single pulsar seems to be very close to Gaia stars. And when I say very close, I mean sub a tenth of an arc second close. So that's very close. So there should be some hidden binaries in there, and even if this turn out to not be binaries, I think still having a very uniform data set such as yours should be excellent for constraining the binary fraction. And
it's kind of difficult to comment on these things because they're sort of happening at the moment. But one thing I can tell you is that the our measurements of F1, so F dot, nu dot, whatever you call it, as a function of time, reveal different classes of pulsars, and some of them appear to have periodic or near periodic F dots. And the way we're doing the F dot measurement using Gaussian processes, it's quite insensitive to timing noise of other types. So there's some possibility that well, of course there's uncertainties in the position and proper motion in there that would come out through F dot, but there's also possibilities that there are other things that we can catch with this. But it's all sort of happening right now.
Okay, thank you. So